As always, let's thank Localytics for the wonderful space and for hosting us.
Welcome everybody. Thanks for taking your time to come tonight. Hopefully we will learn some stuff about Bayesian optimization, Bayesian statistics. I work at Localytics, where you all are right now, heading up our products in data science and machine learning. And so we're focusing on three key areas: predicting app user behavior. The second is in recommending app users content and products to consumer purchase, and the third is in optimizing all of the above. And funny enough, on the optimization side, we are using some Bayesian methods as well, working on problems related to the multi-armed bandit. We are building the tools and analytics infrastructure to power some of the most popular mobile applications in the App Store today, and we are investing very heavily this year in data science and machine learning. If anyone saw our funding announcement earlier this week, just raised a sizable amount, and a big investment for us this year is going to be in, as I said, data science, machine learning. So if anyone's interested in learning more about that, I'm available while we're eating pizza or even after the second talk to talk to you more about that.
So our first speaker is Alan Downey, who's going to talk about Bayesian statistics and German tanks.
That's the plan. Let me a quick introduction. I teach out at Olin College, which is in Needham. It's a new college. We're trying to fix engineering education. We've been at it for about 15 years. We've almost got it. There's just some pictures from me doing some teaching out there. The plan for today, what I want to do is start with first principles, develop Bayes Theorem, and get from Bayes Theorem to Bayesian statistics. My theory here is that I can start with the basics and in 30 minutes get to a real-world problem, a life or death problem that actually came up during World War II, which is the German tank problem. So I'm going to start with Bayes Theorem. Bayes Theorem is on my list of desert island algorithms. These are things I believe that I could have invented given enough time and no resources. I came up with Euler's method all by myself. I invented Kaplan-Meier estimation about 20 years after it was invented. And I think I would have come up with Bayes' theorem. The thing I would not have come up with is Gödel's incompleteness theorem. No one would have come up with Gödel's incompleteness theorem. So starting from first principles, definition of probability, I'm just going to say that there's some event, either past or future, you don't know whether it happened or not, and there's some probability that it happened. So P of A, probability that A occurs. The conditional probability, P of A bar or pipe or whatever you want to call that thing, conditioned on B, that's the probability that A occurs given that you know that B occurred. And then the conjoint probability, if you want to know whether two things happened, a probability of A and B is just the probability of A times the conditional probability of B given that you know that A happened. All right, that's my starting place. The next step is to recognize that that conjoint probability commutes. So you can write it either as probability of A and then the conditional probability of B, or the other way around. Maybe somebody tells you that B is true, and then you check A second. It doesn't matter what order you check in, you should get the same answer either way. So if you take my equation 1, take the right-hand sides, and set them equal to each other, you get equation 2. So far, arithmetic, nothing too frightening, I hope. And if you divide through by the probability of B, congratulations, you've just proven Bayes' theorem. So, thank you. So the point of this, first of all, is that this is fundamentally a simple idea. It's a direct consequence of the definitions of probability. The other thing that I would say is that there's nothing controversial about Bayes' theorem. So you might hear, Bayesian statistics, some people love it, some people hate it. Nobody is controversial about Bayes' theorem. It's just a true statement of mathematics. So there it is. There are two ways to think about what it is. So one way to use it is as a divide and conquer algorithm for figuring out a conditional probability. Sometimes the left-hand side of that equation is hard. If you don't know probability of A given B, you can figure out the other things on the right-hand side. If you can figure out probability of B given A, probability of A, and probability of B, then you can use that as a divide and conquer algorithm for figuring out the left-hand side. And there are lots of nice examples that you see in probability classes where the left-hand side is kind of not obvious, but the three terms on the right-hand side, no problem, you can figure it out, problem solved. So that's one way to think about Bayes' theorem, but it's not the primary way. In the context of Bayesian statistics, you're usually thinking about the diachronic interpretation of Bayes' theorem. Diachronic is just Greek for through time, and the idea here is that you start out with a prior set of beliefs, you see new data, the data causes you to revise your beliefs, and your revised beliefs become your posteriors. In the notation that I'm writing, I'm going to use H for the hypothesis that you're not sure about, D for the data that you see, and we're going to start with a prior, P of H, that's the probability of the hypothesis before you see the data, and try to figure out a posterior, which is the probability of the hypothesis after you see the data. Good so far? I should have said at the beginning, if you have questions, interrupt me. I'm going through this kind of fast because I'm assuming that at least some of it is familiar, and I want to get to the good stuff. The good stuff is the cookie problem. So this is the first problem that you always see when you learn Bayes' theorem. Sometimes it's an urn full of marbles, but more appealing if it's 2 bowls of cookies. So I've got 2 bowls of cookies. One of them is 50-50 vanilla and chocolate. That would be, let's see, that's bowl 2. Bowl 1 is mostly vanilla, 3/4 vanilla. So you choose a bowl at random, and then you choose a cookie at random from that bowl. It turns out to be a vanilla cookie. And what you'd like to know is what's the probability that the bowl you drew from was bowl number 1. Okay, so we're going to apply Bayes' theorem to this, give you a sense of how this works. So I'm going to state my hypothesis. H is the hypothesis that the cookie came from bowl 1. D, the data, is that I got a vanilla cookie. I've got my prior. I'm trying to compute a posterior. So here's what that's going to look like. There's Bayes' theorem up at the top, just written in a little bit more concise form. There's my definition. P of H is the prior. P of D given H is the probability of the data given the hypothesis. So this is kind of backwards from what I'm trying to figure out. My posterior is the probability of the hypothesis given the data. P of D pipe H is the likelihood of the data given the hypothesis. And then my denominator is the total likelihood of the data under any hypothesis at all. As I mentioned a minute ago, divide and conquer, we can figure out each of the pieces easily and then just put them together. The prior in this case is easy because I said I chose the bowls at random. Let's assume that means 50-50. So I've got my prior. The conditional likelihood of the data says if the bowl is actually bowl number 1, what's the chance of getting a vanilla cookie? That's 3/4 because we know that bowl 1 is 3/4 vanilla cookies. And then the denominator in this case is relatively easy to figure out because you can mentally take the 2 bowls and just combine them. And what you find is that 5/8 of the cookies are vanilla. So the chance of a vanilla cookie under any hypothesis at all, in this case, we can kind of do a shortcut and figure out that it's 5/8. In general, you have to do a little bit more work that I'll show you. So there are the 3 pieces. Put them together, and you figure out that the result is 3/5, so 60%. Having seen 1 vanilla cookie, you are now 60% confident that the bowl you drew from is bowl number 1. Just to get a feel for that, you started out thinking it was 50-50. The data moved the needle just a little bit. You now think that there's a 60% chance that it's bowl 1. That makes sense because the vanilla cookie was more likely to come from bowl 1. So the existence of the vanilla cookie makes you think it's more likely that it's bowl 1. What Bayes' theorem does is tell you how much more likely. So part of what we're doing here is quantifying the kind of thinking that we do intuitively. Okay. So I want to introduce a computational framework for doing this stuff. My thesis here is that a lot of the Bayesian statistics that is hard to do mathematically is really easy to do computationally. And I talked to some of the people here before I started, and it sounds like most of you are familiar with Python. I'm going to show you some Python code. Even if you don't know Python, this should be pretty readable. The idea here is that I've taken a Python dictionary and I've wrapped it up in a class that's called a PMF that represents a probability mass function. If you're familiar with Python dictionaries, you can think of them as a map from a set of keys to a set of values. In this case, the keys are all the possible outcomes of an experiment, and the values are their probabilities. So this is a map from possible outcomes to probabilities. All Bayesian stuff basically fits this framework. You build a PMF that represents your prior beliefs. You do an update by computing the likelihood of the data under each hypothesis, and then multiplying each prior by its likelihood. And then you have to renormalize, because once you've done the step 2, your probabilities don't add up to 1 anymore. And so it's not a proper PMF anymore, but when you just divide through by the total, then it all works out. If you're familiar with some of this background, that probably made sense. If not, let me show you the example. So here's the cookie problem again computationally. I'm going to create a PMF object. Again, think of that as a map from each possible hypothesis to its probability. So initially I'm using strings, bool1, bool2, to represent the hypotheses. This is Python. You can use any data type you want to represent hypotheses. And I'm starting with a prior that says they're both 50-50. So there's my prior. I'm going to update with the likelihoods. So I compute the likelihood of a vanilla cookie given that it's bool1, the likelihood of the vanilla cookie given that it's bool2, and then just multiply through by those likelihoods. What I have now is a PMF that's not normalized anymore. Now it's normalized. I've got a function called normalize. It does exactly what you think. It just adds up all the probabilities and divides through by the total. So now the sum has to be 1, and the posterior, and what you have now are the posterior probabilities. And what you see there is that the bool1 hypothesis maps to 0.6, which is what we got when we did it by hand, and bool2 maps to 0.4, which it has to because they have to add up to 1. All right. That's the end of the cookie problem. I should pause there. Any questions about cookies? All right, so I'm going to do this incrementally. I'm going to sneak up on the German tanks. We're going to do the dice problem, the train problem, and then we'll do tanks. So here's the dice problem. I have a box of dice. I've got a 4-sided, 6-sided, 8-sided, 12-sided, and 20-sided die. I choose one at random, and let's assume that means equal probability. Choose it at random. I don't let you see it. I roll the die. I get a 6. And now my question is, which die did I roll? Okay. So this is a little bit similar to the cookie problem in being an inverse probability. What I'm going to use to do this is a slightly different object, another Python object called a suite. This is very similar to the PMF, except what I'm going to add to it is some of this framework, the Bayesian framework for doing these updates. I'll show you what that code looks like. So here's what a suite is. It's a PMF. The only thing I've added now is an init method that's going to take a list of hypotheses. It gives them all the same probability. It starts out by setting them all to 1, and then it normalizes. So this, by default, assumes that you're going to start with a uniform distribution where all of your hypotheses have the same probability. It doesn't have to. You can override this if you want a different prior, but we're going to start out uniform. The other thing that the suite class provides is an update function. And what update does is it loops through the hypotheses, computes the likelihood of each hypothesis, and then multiplies by that likelihood, and then renormalizes. So this function encapsulates the same process we did a minute ago with the cookies. The nice thing about this is that this function is the same for pretty much all Bayesian problems. The only thing that you have to provide is the likelihood function. So the likelihood function in this framework is an abstract class. Python doesn't really have abstract classes, but I'm just faking it. This is a class definition where suite provides everything you need except likelihood. And what you do is provide a child class where you inherit everything from suite, you provide likelihood, and then you're done. So I'm going to create a dice class, and then I'm going to define a likelihood method for it. What we have to do is figure out the likelihood method. So here's what we can think about. The outcome was 6. If the die I chose was a 6-sided die, then what's the chance of getting that outcome?
6th.
1 in 6, 1/6. Right? Okay. What if the die that I chose was the 10-sided die? What would be the chance of getting a 6? 1 in 10. Okay. What if it was the 4-sided die? What would be the chance of getting a 6?
0.
0. Can't happen. So if I get a 6, I can rule out the 4-sided die. It can't have happened. And then for the others, I can figure out the likelihood. Here's what that looks like. I'm going to define a new class called dice. It inherits from suite, so it gets the update method from suite, and I provide likelihood. Likelihood takes two parameters, the data and the hypothesis, and my job is to compute the likelihood of the data under the hypothesis. The hypothesis is the hypothetical number of sides on the die, and the datum, in this case, is the outcome of the roll, the 6. So if the hypothetical number of sides is less than the outcome, well, that can't happen, so I return 0. Otherwise, the likelihood is 1 over the hypothetical number of sides. That's it. That's the likelihood function. And the nice thing about this whole Bayesian thing is that once you've figured that out, you can turn your brain off. The good Reverend Thomas Bayes comes from the grave and does all the work that's left over. So here's what that looks like. I'm going to create a suite. I'm going to start with 5 hypotheses. Is that 5? Yes. In this case, I'm representing the hypotheses using integers, but that's all right. I can use any Python type. And I'm going to do an update passing the datum as the argument to the update, and then print the suite. And there's what it looks like. Okay? So the 4-sided die has been ruled out. It has posterior probability 0. The 6-sided die is about 40%, 30%, 20, 10-ish. Okay. The higher valued dice are less likely because any particular outcome is less likely the more sides you've got. So that's what that outcome looks like. This is a simple example because I've only got one datum. Here's another nice thing about the Bayesian analysis. If you know how to do one update, you know how to do all of the updates. If you roll the die more times, assuming it's the same die, so I picked my die, I keep that same die, I roll it over and over. Let's say that I rolled the 6 to start with, and then I get 8, 7, 7, 5, and a 4. Well, what do we know at this point?
It's not the same.
It's not the 6. So 4 has been ruled out, 6 has been ruled out. What would be your guess?
Most likely.
It's kind of looking like the 8-sided die. How confident would you be? Ballpark, 75%, 80, 90? What do you think? I'm curious to know what your intuition is like. As I said, the Bayesian update is kind of quantifying what we do intuitively. What does your intuition say? I'm hearing 0.9-ish?
No, more than 0.39.
More, definitely more than 0.39. It's very conservative.
But there's a 10-sided die too.
There is a 10 in the game, and the 10 has probably not been ruled out. It's a little bit surprising that we haven't seen a 9 or a 10 yet, but not that unlikely. Good. Let's take a look. Here's what the posterior looks like. Oh, sorry. You had me going. For this particular example, there is no 10-sided die. Yeah, 12 is the next one. So just with the data we've seen, with 6 rolls of the die, we have eliminated 4 and 6. 8 is looking very likely, a little bit more than 90%. 12 is not out of the running, a little bit less than 10%. 20 is surprisingly low, at least to me. My intuition wasn't quite ready to rule out the 20-sided die, but the good Reverend is telling me the 20-sided die is pretty much out of the running. Okay? Unless the next roll is a 20. Or a 13. Anything 13 through 20 would change this radically. The 4, 6, 8, and 12 would instantly become 0, and the 12 would instantly become 1. So I shouldn't have said ruled out. What I should have said is unlikely at this point, but you never know. All right. That is the dice problem. Any questions about dice? Good so far, yes sir.
Why the sum was not 1?
Why did it not add up to 1? It probably got rounded off. Is it approximately 1? Yeah. 92 and 8 and a little extra. I must have rounded up. Good. Okay. Next problem is called the Trainspotting problem. Trainspotting used to be a hobby where you would go to the rail yard and you would watch the locomotives and you would write down the cards, and it was kind of like a collection game where you would compete to see who had seen the most trains. So here's the idea. You have a prior belief about a particular carrier. So let's say you work for a rival company. You want to know how many locomotives they are operating. Because of background information, you're pretty sure that they have somewhere between 1 and 100 locomotives. So that's your prior. And you think it could be equally likely to be any value in that range. You go down to the rail yard and you spot locomotive number 21. And furthermore, you know that this rival company has numbered their locomotives from 1 to however many they have. Okay? So the question now is, how many locomotives do you think they have? The computational framework for this is going to be exactly the same. I'm going to create a new class called train. I'm going to inherit from suite. So I've got the update method. I know how to do a Bayesian update. The only thing I have to do is figure out the likelihood function. So here's your homework. Fill this in, or I'll do it for you. So you've got a hypothetical number of trains that you think they have. So if they have n of them, then they will be numbered 1 to n. Right? So if you see a train that is numbered higher than n, well, you can rule out that hypothesis. And if you see a number that is less than n, the probability of seeing that particular train is 1 over n. This might seem familiar to you. This is exactly the same likelihood function we were just looking at with the dice problem. The only thing here is that it's kind of like we have a lot more dice. We have 100 different kinds of dice with 1 side and 2 sides and 3 sides. I don't know what a one-sided die looks like. But here's how the framework works. I'm going to create a list of hypotheses from 1 to 100 and 101 exclusive. And then I'm going to create a train suite that has those hypotheses as the priors. And then I'm going to do an update with train number 25. Before I show you what the posterior looks like, think about it for a second. I'm going to go have a beverage, talk with your neighbor, and see if you can figure out what this posterior curve is going to look like. You've seen train number 25. So notice that everything below 25 has been ruled out. The probability is now 0. Between 25 and 75, it looks kind of like a 1 over n curve, except it's kind of a funny 1 over n because it's been truncated at 100. So all of the probability weight that would have been above 100 has to be squished into this zone. And all the probability weight that was between 0 and 25 has been squished in. So it's 1 over n with truncation and then squishing.
And 0 before.
That's the technical term. Comes out looking like that.
Multiply by.
Same thing I mentioned before. If you go back the next day, you see train number 42. The nice thing about this Bayesian framework is that more data is just as easy as less data. You just iterate. So loop through the data, 25, 42, and what you see is a curve that looks like that. So the left-hand curve there, that's the one we were just looking at a minute ago. That's what you believed after seeing train number 25. Then you go down to the rail yard, you see train number 42, and you update your belief to the thing on the right. So that's now dropping off like 1 over n squared with truncation and squishing. Okay? And that is pretty much it for the train problem.
Alan,
Yes?
Just to reiterate what you said before about you can do those in either order.
Yeah.
If you got 42, then 25, you'd still end up with the same curve, correct?
That is correct. And that is true in general for these updates. It doesn't matter what order you consider the data in, you get the same answer. Yes?
This is the same curve.
Oh, sorry, go. Up front and then back. Yes?
It's the same curve as if you didn't ever get that 25 as a first result. If your first row is 42, you get this.
Not quite. So the question, if you didn't hear it, is this the same curve you would get if you only saw train number 42 and not train number 25? Not quite. You're partly right, which is that the maximum is kind of the only part that you need to know, but you also need to know how many trains you have seen. So the blue curve, the second curve, drops off more steeply. It's like 1 over n squared because you've seen 2 trains. Good question, thank you, and yes.
Just a side note, given that you already saw any time it's gone, you can't see 25 again, everything changes is dependent.
Ah, okay, the question was, if I see train 25 and it's gone, should I take it out of the pool? This is I could do it with or without replacement. In this case, my numbers are big enough that the difference is not going to be very big. In other cases, you're right, it's going to be important to be clear about what my sampling process is. So good, thank you. Anything else about trains? All right.
And if you looked at it for a long time and you saw lots of trains, how would the curve look like at the end of 100 trains?
Good question. After 100 trains, let's say that in fact the company has 88 trains. Right. So the highest number I've seen is 88, and I've seen many, many trains. So at that point I would conclude that if they had a train that was higher than 88, I would have seen it by now, and I will have almost ruled out all of the others. So after 100 trains, I would have a spike at whatever the highest number train is that I've seen. Yes?
If you did 100 trains without replacement,
if I did 100 trains without replacement, I think
they have 100 trains.
Also, well, I'm assuming that, oh, sorry. Yes, good. Okay. So two things we've discovered. One is that the dice problem and the train problem are exactly the same. There is one other problem that is also exactly the same as the dice problem and the train problem. That is the German tank problem. This is a Wikipedia page. You can read all about it. It's good stuff. I'm going to give you the quick introduction. The general idea is during World War II, when the Allies captured a German tank, they would take it apart and record the serial numbers that were on all the parts. The chassis, gearbox, and engine numbers were uniquely given serial numbers, and the wheel molds, the wheels were not uniquely numbered, but the molds were. So you knew which mold each wheel came off. And it turned out what they discovered, I don't know how they learned this, but they knew that the serial numbers were being allocated to given factories. So a factory would have a block of serial numbers that they would use for a month. And if they filled up the block and used it up, then they would go get another block. But if they didn't completely use the block, then those numbers would go unused. So it was kind of like IPv4. There was a lot of unused space. What that allowed you to do was to estimate, of all the numbers in a given block, how many of them are in use. And you might recognize that this is looking a whole lot like the train problem at this point. You've got blocks of 100. You know that they're partially used starting from 1 up to an unknown value of n. And now you can estimate of the 100 in each block, what fraction of them were actually used. So Ally spies were doing this during World War II. After the war ended, they went and captured the records, and they were able to validate the predictions they made during the war to see what was actually going on. And it turned out that they had done remarkably well. So the left column is the predictions. The right column is what they learned was the truth. The middle column is what the conventional intelligence was yielding. The conventional intelligence was way too high. The Bayesian estimates were remarkably good. So this was a triumph of Bayesian statistics. It actually goes a little farther than that. Often when you read about this, the punchline is that the estimates were accurate. And that is a nice thing about Bayesian statistics, but it's actually not the best thing about Bayesian statistics. The best thing is that when you do the Bayesian analysis, the result is not a single point estimate. Like, my best guess is 149 tanks. It's not even a confidence interval. Like, I think that there's some likelihood that the correct answer is in this range. What you get is a posterior distribution. The posterior distribution represents all the possible outcomes and their probabilities. And this is exactly what you want for doing any kind of decision analysis. If you want to do a risk-benefit analysis or cost-benefit analysis, what you want to be able to do is loop through all the possible outcomes and know how likely each of them is. So you can compute the expected value of whatever the process is that's downstream from that. So this is my attempt to kind of sell you on Bayesian statistics, not just because you get the right answer, but because you get the answer in a form that lends itself to solving real problems, the posterior distribution. I want to dispel one other Bayesian myth that you might hear, is that, yeah, Bayesian methods are great, but they're hard. You have to know a whole lot of advanced math, and before you can do the Bayesian stuff, you have to learn all the classical stuff first, because it's a graduate topic. Okay? This is not true. With computational methods, you can, in the space of about 30 minutes, get from deriving Bayes' theorem to solving an actual problem that was a life and death problem during World War II. I have one other piece of evidence for this, which is that I teach a Bayesian statistics class for undergraduates. The people coming into that class, they're usually sophomores. They've taken Python, so they've got some programming skills, but they usually have not had a statistics class before they come in. So I'm teaching Bayesian statistics as a first class, forget about the classical stuff. And what I found is that after 7 weeks, it's only a half semester class. After 7 weeks, they are able to apply these methods to real-world problems and come up with some really nice solutions. If you're interested, this semester I'm publishing some of their results in my blog as a way to kind of prove this thesis. It's like, look, undergraduates, here's what they're doing. We just did one this week. My blog is called Probably Overthinking It. So look it up, and you'll see the most recent one that I posted is 2 students who did survival analysis for the characters in Game of Thrones. And they're making predictions about who will survive the next 2 books. Of course, the follow-up question is, will George R.R. Martin survive the next 2 books? All right. Everything that I just presented is in chapters 1 through 3 of Think Bayes. If you want to check that out, it is at thinkbayes.com. There's a free version there. It's also published by O'Reilly if you want hard copy. I've got a copy of it with me if you want to check it out. Last thing I'll mention, this summer I'm thinking about trying out some Bayesian boot camps in July and August. And part of what I'd actually love it if you would do is just give me a sense of how much interest there is. My intention is to do either half-day or full-day workshops, tutorial style, where you've got laptops, you're running through some hands-on examples. We would kind of do similar to what we just did, but more, and you would get to do more coding. If you're interested, I've got a link there. That's just a survey. If you'll just let me know, who you are and whether you'd be interested or not, that'll give me a sense of whether I should try this or not. So that's that bottom link. The middle link is these slides. So if you want to grab the slides, there's the tiny URL. And if you want to contact me, there are 4 ways to contact me, all kind of crammed in there. Questions? So one of the challenges of Bayesian statistics is that the posterior depends on the prior. And not everybody necessarily agrees about what the right prior is. So there's often some subjectiveness that makes people very nervous. There are 2 reasons to not be too nervous about that. One of them is, very often you do have background information that lets you choose a prior in a sensible way that most people would agree with. So very often you can get people to agree about the priors. The other thing is, even if they don't, if you accumulate enough data, then people who started with different priors will eventually converge to posteriors that are close enough that nobody cares about the difference anymore. So that's the convergence. And then the third thing is, yep, it's subjective, get over it. Yes?
I have a question along the same lines. I guess if you're using it, maybe I was referring to using it to think about when you have a new scientific experiment that gives results, then you're thinking, well, before we thought this, now we have this experiment and we think this. There seems to be a lack of a parameter in the Bayesian statistics approach to that, in that there's no way to say how confident you were before this experiment. So you have a prior probability, and I realize higher could mean more confident, but there's not really a parameter to say how sure you are about your prior. Do you think that's a lacking thing, or am I missing something about how to use it?
Right. It is often the case that you can express your prior beliefs using second-order probabilities. So you could say, for example, I think there's a 75% chance that this will happen, but I'm not sure that 75 is the right number. It might actually be 65 or 85, or whatever. Yes, you can do that in a Bayesian framework. It is often the case that your second-order probabilities will collapse down to first-order probabilities. But even if they don't, there are still ways to work with it, like hierarchical Bayesian models.
Okay, so you're saying you could basically add in what I was talking about if
Yeah.
you do some more complex stuff.
You can have your beliefs about your beliefs about your beliefs, and it's turtles all the way down.
Great.
I have a
Yes.
question. Oftentimes when we're talking about machine learning problems, we're dealing with more than a handful of die or hundreds or thousands of trains even. Can you talk about how Bayes compares to Bayesian methods compared to other methods for processing and interpreting data at scale? How is it? What are the costs and benefits of running these things on millions or billions of data points?
That's a great question. If you couldn't all hear it, the question is, how do these things scale? The examples that I gave here are all small data examples, and that's one domain where the Bayesian stuff does really well. You can kind of wring all the information that's available out of your data. But the methods that I'm using here and what I present in Think Bayes is meant to be conceptually easy, conceptually accessible, but the performance is usually terrible. What I'm doing here is pretty much a brute force solution to these problems. But there are a couple of steps that you can take to get things to scale up. So I do brute force. The next step up from there is things like Monte Carlo Markov chain, MCMC, which is implemented in PyMC. Very often the stuff that I've done can be translated into PyMC in a very straightforward way, and you'll get speedups that are unpredictable because the nature of the problem is going to determine how well these things perform. And then the next step is to replace some of the computational stuff with analytic methods. So some of the things that for me are linear time algorithms, because I have to go through all the hypotheses. With analytic methods, often you can do that in constant time. So one example of that is estimating proportions. If you want to know how often something happens, the beta distribution comes to your rescue. And then you get into what are called the conjugate distributions, and then you kind of get to the math part that I was telling you didn't have to do. So sometimes to get the performance, you do have to do the math.
Thanks a lot.
Thank you all very much.